Hello everyone. This section I will talk about SRAM. SRAM is a common used cell in digital circuit, so you have to understand the behavior of SRAM and how to use it properly. In this section, I will introduce the three common types of SRAM: single port, two port, and dual port. And last, I will give you some suggestions on the usage. So typically, SRAM is a micro, a hard micro, or you can say an analog or mixed signal micro, and usually it will be generated by memory compiler. And memory compiler is a tool, is a software released by the IP vendor, by SRAM IP vendor, such as the Foundry or IP vendor like ARM. So it's a hard micro. You can use it, but you can't synthesize it. Okay. Okay. Let's say the block diagram and the function of a single port SRAM. To single port, it means it just has one address input. Yes, it has just one address input. So and only one data input and data output. By the way, the function of SRAM is store some data. Yes, you can write some data in and then read them out sometimes later. Okay, this is the function of SRAM. Store data. And power up. The value in SRAM is unknown. That is, every address of SRAM has a value, but a random value. You can't predict what the value is, and usually there is a low reset pin. There is a low reset pin for SRAM micro. So the usage of SRAM is we first write to a location, then read it back. First write, then read. It's acceptable if you read it before write, but the returned value will be a random value. You can't predict what the value it is. Okay, this is the general description of SRAM. So let's say the function of single port SRAM. Let's first look at the waveform of write. For write, you have to assert the chip select and the write enable. Yeah, assert it to the active state. Usually, you have to take a look at the data sheet. In this figure, they are high active, but for a micro generated by memory compiler, they may be low active. So you have to check the user guide before use it. Okay, assume they are all high active, so you have to assert chip select and write enable and give address and data. They are aligned in the same cycle. So this cycle will write D into address 0, and the next cycle you can continue do a write operation. Then you keep CE and WE high and give another address and data. Then at this edge will write D1 to address 1. And it's a random access memory. So after this address 0, you can change address to 1000. Okay, any address is okay. So if you give 1000, then D1 will be writing 1000. Then you can change another address. And this cycle, D2 will be writing in address 2. The key point here is you have to assert CE and WE high and along with address and data in the same cycle. And for write, most likely the write data will bypass to D out. The write data of last cycle will bypass to the D out and next cycle. Yeah. So the write data, the write operation of cycle n, the write data of cycle n will bypass to the D out and cycle n plus 1. Yeah. Yeah, this is the value bypassed, the write data bypassed to D out. Okay. And for some cells, it has an actual input coded byte enable, or you can say bit enable, write byte enable. That is, it can control which bit or which byte will be updated for this cycle. For example, if the D in is 32 bits and we have byte enable of 4 bits, then if we let byte enable to hex of F, so at this cycle, all the 32 bits will be updated to address 0. Okay, but for this cycle, if we give to, okay, so only the least significant 8-bit, the lower 8-bit will be updated, and for the bit 31 down to 8 into SRAM, the value of this bit will be kept in SRAM micro, will be not changed. Okay, so this is the function of write byte enable. It can control how many bits or bytes you can update in this write operation. Of course, you can give any combination of write BE, such as, yeah, this is also okay, any combination of, and if you give all 0, that means low bits will be updated. This is an NOP operation. Yes, just an NOP operation. Okay. So let's check the read operation. For read, you give the chip select high and you put write enable to the inactive state. In this figure, we drive it to low. Then you give address. But the read data at D out will be 1 cycle later. Yes, will be 1 cycle later than the read operation. So you read and cycle n, and you will get the read data and cycle n plus 1. Read here, read and this random age, then you get data at the next random age. Yeah. So this is the difference between read and write. For write, address and data are aligned at the same cycle. For write, they are aligned at the same cycle. For read data will be 1 cycle later than the read operation. Okay, so this is the function of single port SRAM. And please take care of the write effect on the D out. Yeah, that is, if you read first, you get the read data here, and next cycle, and if you write at this cycle, the D out will be changed. Yes, the D out will be changed. That is, the write data will bypass to D out and next cycle. Okay, so you have to mention the write effect on D out. Write operation will change the data on D out. This is most likely case. Okay, I think more than 95 probability, and you are suggested to read the user guide to check the behavior of write operation before use it. Okay, read the user guide. Okay, this is very important. So from this figure, you can see for single port SRAM, you can mix read-write. They can't happen in the same cycle, just at a different cycle. For every cycle, you can choose read or write. Next cycle, read or write. You can choose it by your own. There is no restriction of read-write between each cycle. Okay, while for FPGA micros, okay, the write effect on D out may have two behaviors. That is write bypass. This is the figure we see here. Yeah, the waveform we see here is write bypass. Write data will bypass to D out. And FPGA also have the behavior of write no change. That is, the D out will keep. This is your read operation. Yes, write edge, read operation. The D out will keep. Even there is a write operation. Yes, this is a write operation, and the write data will not bypass to D out. Oh, sorry. Will not bypass to D out. So this is called write no change. So only read operation will change the value. Only read operation will change the value on D out. But for compatibility, it's recommended to design as write bypass mode. Yes. So for write bypass mode, most likely this design can be used in ASIC mode and FPGA mode. And if you want the behavior of write load change, you can add your own logic around the SRAM micro, then make the write load change behavior. So that means this is a write bypass micro. You can add some logic here and add some logic here and make them a write load change behavior module. So how to design this? Yeah, this is you can try to figure out how to design this using the write bypass memory micro and design a write load change behavior module. Let's say the behavior model of single port SRAM. So for single port SRAM, you can write a behavior model for simulation like this. This is parameter defining the depth and bit width. So you define the memory here, and this is the write operation, this is the read operation, and this is write bypass. Okay, this is the behavior model. Can be used in simulation. This is a simple behavior model. Okay. And if you want something like write enable, you can check this model. Okay, we have the write byte enable input. So this is the function with write byte enable. It will control which bit will be updated. The memory is a 128-bit memory. The bit width is 128. The depth is 32. Okay. So in this model, each bit will control whether you will update the 64 bits or not. Okay. And the two model, when you use it in ASIC, you just use this model to simulation. Okay, in simulation, you can't synthesize it. If you use it to do synthesis, this will be synthesized to register. Okay, register, not memory micro. So you have to use memory compiler to generate the micro and ASIC application. But for FPGA application, the two module can be synthesized by FPGA tools. This is because there is memory micro inside the FPGA device. So this FPGA synthesis tool can map this model to the memory micro inside the FPGA device. Okay. So after you have understood the behavior of single port SRAM, two port SRAM is almost the same. Two port SRAM usually has two ports as is SRAM. Usually one port is read only and one port is write only, so it will have two address. And one port is write only and one port is read only. Okay. And the write data here will not bypass to the read port, will not bypass to D out B. Okay, there are two independent ports. And for two port SRAM, for a single cycle, you can do both write and read in a single cycle. Yes, for example, for cycle N, you can do write to A0 and do read to A1. This is legal. But you need to take care of that. If read write to the same address, the behavior will vary from cell to cell. That is, the D out may be a random value, or the write operation may fail. So, for compatibility reasons, designer must avoid this situation. That is, you must avoid read-write the 2-port SRAM of the same address in the same cycle. So that is, you can't, for cycle n, you can't write address 0 and read address 0. This is typically not allowed. And the waveform of write and read is the same as the single-port SRAM. Okay, just take care of these restrictions. Don't read-write the same address at the same cycle. And for 2-port SRAM, write data will not bypass to D out of B port. And the clock A and clock B can be connected to different clock source. Yes, for single port, you can say we just have one clock input here. But for 2-port, usually you have 2 clock input. So they can be connected to different clock source, such as we can connect it to 100 megahertz. Okay, and we can connect this signal input to 89 megahertz clock. Okay, you can connect it to different clocks. Okay, this is for 2-port. Then we have dual-port SRAM. What is dual-port? It also has two address. Yeah, two address. But the function is for every port, for port A and port B, they can both read and write. Yes, this port can do read-write operation, and this port can do read-write operation. This is the difference between two-port and dual-port. And the write data on A port will not bypass to the D out of B port. Yeah, the write data of A port will only bypass to the D out of A port, but not the D out of B port. And this is the same for B port. Okay, write data on B will bypass to here, but not here. Okay, there is also the same restriction for dual port. You can't read-write the same address and the same cycle. The behavior will vary from cell to cell. That is, for different memory compiler, the behavior will be different. So for compatibility reason, designer must avoid this situation. But for dual port, if you read the same address on AB port at the same cycle, this is okay. Okay, the two read must be successful, and there is no side effect if you read the same address and same cycle. But if there is one write, one read for the same address and the same cycle, this is not allowed. And two write on the same address of same cycle, this is also not allowed. Okay. This is allowed on the same address. Okay. Okay, let's say the model. Let's say the simulation model of two-port. Okay, you define the signals, the I/O signals here, A port, B port. Then you write on A port and read on B port. And the write data here will not bypass to the D out. Okay, this is a two-port SRAM. Two-port SRAM. There is no dual-port SRAM here. Okay. So for the behavior model of dual port, typically you just double this code block. Yes. One code block for port A and the other code block for port B. Just double it. It should be okay. And change the signal names. A, then B. Okay. Okay. And by the way, ROM, read-only memory, can also be generated by memory compiler. For ROM, okay, let's say the ROM. This is the ROM. There is a ROM. So for ROM, it has just clock, enable, and address and D out. There is no write enable and no data input. So the behavior model is just read operation. So what's the data? What's the data in the memory? So you have to initialize the data in the memory. Yes. So for simulation, we use the initial statement and along with the read memory B or read memory H system call to initialize the data in a file to the memory cells. Let's look at the initial data file, just a single txt file. Yeah. Okay, this is a file. You just list the value of each address line by line. Okay, so this is the value for address 0, address 1, address 2, address 3. Yeah. And this is a 9-bit memory. Bit weights equal to 9. So each address you will give 1, 2, 3, 4, 9. Okay. 9 binaries. And you use the read memory B task. There is also a task called, they are almost the same. Just the number here is in the hex format. Okay. Okay. And for this module, this is just only for ASIC mode. This is simulation only, but for FPGA mode, this initial block can be synthesized, or the whole module can be synthesized. Okay. For ASIC, if you want to use the ROM in ASIC, when you compile the ROM, you also need to give an initial file to the compile tool to set the value of each address. Then the tool will set the value of each address for the ROM. So after manufacture in foundry, and power up. When the chip is power up, yeah, the value you have been set can be read out from the ROM. Okay. Okay, there is some usage suggestions. The first is try to use single port SRAM. This is for a consideration of area. Typically, if the bit size is the same, that is the width, the data width multiplied depth. Okay, so if you have you have a 32-bit wide memory with 1024 depths, then the area of single port SRAM will be much smaller than 2-port or dual-port SRAM, usually in the 1.3 to 1.8 times. If the depth is smaller, the difference will be bigger. If the depth is bigger, yeah, the difference will be smaller. Okay, this is the relationship between the size difference and the depth. So try to use single port SRAM to save area. So this is a question for you. If the function of the design requires me to read write at the same cycle, is there any way of avoid using 2-port or dual-port SRAM? For example, if the read-write address is in incremental order, such as the OR in the incremental order, the address for read will be 1, 2, 0, 1, 2, 3, 4, 5, then the write address will be also in some incremental manner. Yeah, always incremental by 1. If they have this pattern, the address has this pattern, can you use some method to use single port RAM to replace the dual port SRAM? Okay, one solution is to double the data width. Can you understand? Such as originally is 32, we can double when generated SRAM, we can double it to 64. So for the 32-bit micro, you have to read write such as For example, okay, for example, you have to do it in this manner. So for the 64-bit, you can just, then next cycle we just, for each cycle, we write to data and read to data. Yeah. Yeah. So in this manner, we will change the 2-port SRAM to single port, and this will save area. Okay. And if the read-write address pattern is in a timely manner, okay, let's say the waveform. Okay, this is a 2-port RAM between block A and block B. Block A will write to it, and block B will read to it. But the read-write pattern is in something a timely manner. For example, the SRAM is typically be divided into 2 parts. For this time, block A will write the first half. Then block A will write the second half, but block B will read the first half. Okay, in the timely manner. And when read-write the first and second half, the address may not in the incremental sequence. For example, it may be maybe in something like that. So for this access model, we can split the big 2-port SRAM to 2 small single-port SRAM. Yes, that is in this format. We can split. So for any time, for example, for this time, block A write to this one, and block B read this one. Yes. And for this time, block A will write to here, but this is not read. Block B will read this one. Yeah. Okay, this is a commonly used method to use single-port SRAM to replace 2-port SRAM. And the second is, please put as less combination logic as possible enter the SRAM D out at this point. So please don't put under a subtract here, many if many cascade of marks. Okay. Don't put too many logic delays here. The reason is the CK2 D out delay is about 5 to 10 times that of the CK2Q delay of DFF. So it means it means this time, the CK2 D out delay is 5 to 10 times that of the delay of DFF. So this delay is already very big. So just put as less combination logic at this point. Okay, if you want to do a high-speed design, such as you want to make the clock frequency much higher, so try to put as less combination logic as you can at the D out point. Okay. Yes. So for this CK2 D out delay, you can check the library for the detailed value. Okay. You can check the library of the SRAM macro. So typically, maybe you can there is no combination logic. Just wire click into the out, or you can put a 4 to 1 marks or 8 to 1 marks or something like that is acceptable. And the next is also put as less combination logic as possible and the SRAM input and this input, yeah, as less as possible. So an under of 16B or 32B is not good. Okay, there is no function error, but just the clock will run slower. You can't get a high speed design. So just as less as possible. So for example, a 4-bit under may be still okay. Okay. The reason is one place and root. Okay, one place and root. This is a die of a chip. One place and root, when you usually put the SRAM micros and the outside of this chip. Yeah. When you usually put it here, many micros, SRAM micro and the analog micro. Then your logic, your DF and your combination logic are put at this point and in the middle. Okay, in the middle of the die. So the distance from the driving cell, for example, the cell driving the address, there will be long distance. Okay, so this will cause long wire connections between the driving cell and the memory micro. Then the delay on this wire may be big. Okay. So you can say the output, yeah, the output has also this effect. Yes, the output to the loading cell and the SRAM micro may also place in a long distance. So the wire between the memory layout and the loading cell may also be long. Okay. And to my experience, this is more urgent. Yeah, the output is more urgent than the input. So you can put more. You can put a little more combination logic here. Yeah. But not too much. Okay, but not too much. You must consider the wire delay. The wire delay between the driving cell and the SRAM micro. Okay, the next suggestion is the data values of D in and D out should be the same. For example, they are both 32 or 64. Yeah, they should be the same. If you need something different, okay, you can design your own logic around the SRAM micro to make this function. Such as you want the input of 32 while the D out is 64. You have to design it by your own. The next suggestion is, if the total bit size, that is the wires multiplied depth, is less than 2000 bit, okay, less than 2000 bit or something like that, or something around it, you may choose to use register file to implement this function. That is, you may choose to use register file to do the data memory function. Okay, what is register file? Register file is a memory formed by DFF or latch and can be sensitive. So let's say let's say the model of a rich file. So this is a rich file. Yeah, it's something like the SRAM. Write ADDR input, read ADDR D out, and define the memory variable. And this is the write operation. Yeah, something the same. And this is a read operation. And for read, you can give the combination logic output. So the D out will be the same cycle as read address. Yes. Also, you can add a register after it, then make the same waveform as SRAM. Yes. Okay, this is the rich file. So for small size of memories, such as total bit number less than 2000, you can use rich file. That is just write the code and let synthesis tool to synthesize it for you. Okay. And I want to add one item. If don't read-write the micro, okay. If you don't read-write the micro and some cycles, you must or you'd better put the chip select to inactive state. This is to save the power consumed of the micro. Okay, unselect the chip, unselect the extra micro. Then you can save power. Okay, there is a small question for you. Can you design your test bench to simulate the function of single port, two port, or dual port SRAM? Just give some stimulus and check the result here. Can you write a test bench? If you want to do something more funny or more useful, you can choose to do something like that. Yeah, such as this suggestion, such as this solution. Or can you implement this function? Yeah. From the outside, this is a two-port. Yeah, this is a two-port behavior. But inside, you just instance a single port. You just instance a single port SRAM micro. But with, for example, the input is 32-bit wireless, but with 64-bit wireless micro. Then you make the function. Yeah. This is something more funny, okay? And can you make this? Yeah, this. If you want the input and output is with different data wireless, can you add the logic by yourself? That is, for example, if this is 32, then the read is 16 or 64, but inside this module you just instance a simple single port. Yeah, a simple port SRAM with the same bit width. Okay, the bit width you can choose by yourself. Maybe 32 or maybe 64. Okay, any number, you choose it. Then after you design it, okay, after you design these functions, after you design any one of them, you have to simulate it. Yes, you have to simulate it. Okay, that's all for this section. Thank you.